All right, so now let's take a look at the singular value decomposition from the point of view of the matrices that represent the transformations, and also sort of the geometry about what's going on. They sort of go hand in hand. So remember, okay, we're looking at an operator T, and the singular value decomposition says that the way it acts on a given element is to project that element onto one basis, then scale it, and then use that as the coefficient for the terms of some other basis, right? So in other words, it's taking one ONB to another ONB and then scaling the latter by the, scaling the latter by the singular values. Okay, so now I'm going to use the standard terminology for the matrices here, which unfortunately conflicts with our terminology. So let's see. So if we've got V getting mapped to, or getting mapped to let's actually look at its projection or decomposition in terms of the orthonormal basis here. So this one. Now, if we look at the first part of the transformation, which is to scale each part of this, then what that corresponds to in matrices is we've got some diagonal matrix sigma times some unitary matrix V. Actually, it's adjoint. And so I've got this in red right here because of the conflict in notation. So note this V is an orthogonal matrix. So in other words, the matrix of an isometry. So it's not an inner product space the way that we usually use the notation. Sorry about that. I know it's weird. So we've got singular values coming down the diagonal. That's sigma. And then we've got we've got a matrix whose columns are an orthonormal basis. Then if we take its conjugate transpose, so actually I guess these should be all conjugates because we took V star here. Then its conjugate transpose is its inverse because it's an isometry, right? Okay, so we've got these. And then let's see, so then if we want to look at what happens when we take the matrix of T, so let's call this A, then it's going to be U times sigma V star. So in other words, here we're going to have our other orthonormal basis that we patch on at the end. So if you look up singular value decomposition, like on Wikipedia or something like that, you're going to find it talking about something as a factorization of matrices with this kind of a thing. So you've got some diagonal part where the diagonal elements are the singular values, and then you're going to have an orthonormal basis, or actually the conjugate transpose of an orthonormal basis, and another orthonormal basis over here. Okay, so now the geometry part. What is the geometry part? Well, let's see. So the nicest way to understand it, I think, is sort of what it does to the unit circle. So sometimes it's nice to talk about the unit square, but today let's talk about the unit circle. So we're going to take some unit circle with the standard basis, and we'll say that this transformation here is x gets mapped to a times x. So our transformation is just matrix multiplication. And let's look at a transformation which is a shearing. So it's going to be a horizontal shear to the right. So it's going to stretch this thing into an ellipse. And the ellipse is going to look like this. So notice the blue vector has stayed in place. That basis element has not changed. But this one here has gotten bent to the side. Also, notice that here it's on the top of the circle and here it's on the top of the circle. It's not the point on the ellipse that's furthest from the origin. That's sort of just a nice detail to notice there. So this is something like you would see if you did txy equals x plus y, y, that transformation. Okay, so now what we're going to do is we're going to break this down in terms of transformations. So first, we are going to have the V star map, and so this one is going to rotate the circle like so. And remember, it's a rotation because that's what isometries do. They're rotations and reflections, right? So now we've rotated it because we want to line things up with respect to the standard basis, which here I'm just going to draw in on, draw on in green. So there we go, just for frame of reference. And now we apply the singular value scaling. So it looks like this after we stretch. In the horizontal direction, we stretch by a factor of singular value 1, and in the vertical, we stretch by a factor of singular value 2. Okay. And then we are going to do another rotation by the other isometry, which is switching us back to our other orthonormal basis. And that just rotates things back into position. And so now you can see that this long axis right here, this is the semi-major and semi-minor, or whatever, the long and short semi-major axes of this transformation. Okay. And so let's see. So if we talk more about the way that these matrices are broken down, let's see. So we've got A is given by U sigma V star. And since V is an isometry, its adjoint is its inverse. So multiplying across by V, we have AV is U times sigma. And so written in terms of matrices, this is A times, and then here's your E1 through En orthonormal basis. And then this is going to be, here's your F1 through Fn basis times your diagonal matrix of singular values. So it looks like this. So now if you look at this big matrix equation is just a collection of matrix times vector equations, right? So if we just look at, say, what's going on in the first column on the left side, we have this. What's going on in the first column of the output on the right side? Well, you can see by doing the matrix product of this times this one, and then this times this one, and then this times this one as we go down that first column, we're just going to end up with S1 multiplied by each thing. And so this gives us a system of equations that looks like this. And so you can see now exactly where this interpretation of T is the thing that takes EJ to SJ times FJ comes from. Now, one thing that the book does not get into, in addition to this talk about matrices, the book doesn't talk about how the singular value decomposition works much more generally for linear transformations from one vector space into another. Or, I guess, since it's typically done in terms of matrices, it would be for T in linear transformations from Fn to Fm, in which case we're going to be looking at the matrix of the transformation as an element of I wrote that wrong. M rows and columns. Okay. So let's see. So if we look at some example, let's take T in L from R2 to R3, and we'll take the transformation that does 3x plus 4y, and then minus 16x plus 12y, and then 12x minus 9y. And if you're wondering why these are all such larger numbers than we're usually used to working with, and nice round sort of composite numbers, is because otherwise the if you don't choose nice big entries for your the matrix that you want to decompose, and with nice arithmetic relations between those entries, then you just end up with a whole slew of nasty square roots, and it's a mess. Trust me. So appreciate this. It took me a while to find this example, so it would work out pretty, and not be an ugly disaster. So it's for your benefit that I do these things. Okay. So this guy actually can be written as, let's see, 1 0 0 0 0, and then we've got minus 4/5 and 3/5 and 3/5 and 4/5. Okay, so I'm taking like the first standard unit basis vector, and then for the orthogonal complement, I'm using this sort of skewed orthonormal basis with 3/4 and 3/5 and 4/5. And I'm doing that because 3 and 4 and 5 form a Pythagorean triple, so I don't have a square root in the denominator. So that's how I came up with this example. So then we have a rectangular matrix, and then on the end we have a square matrix, but this is the one for R2, so it is smaller. And I chose the same basis, which just makes things come out a little bit nicer. You can use some other Pythagorean triple, but then your numbers start getting a little bit bigger, and they're already big enough. Look at that, we've got a 25 in here, for God's sakes. Okay, so and so the way that this shakes out, this here, the columns are an orthonormal basis for R3, and then this next guy that you're going to have right here is going to be a quote-unquote diagonal rectangular matrix. So in other words, it's not really a diagonal matrix because it's not a square matrix, but it's the next best thing. So like the A sub jj entries are the only ones that can be non-zero. And so this is going to be a matrix in R32. It's going to be the same shape as the one that you're decomposing. And then this other guy here, this is going to be the rows of this one are going to be an orthonormal basis for R2. And if the rows are, then the columns are as well, because isometry, isometry, isometry. Yeah. Okay, and so, yeah, if you're interested, by the way, I guess I can just throw out here. So if you go back to example 750 that we did before, and we looked at the singular values for it. So this was the one that was 0, 0, 0, minus 3, and that had a 3 and a 2. This guy can be broken down as, let's see, with a minus 1 here, and a 1, and a minus 1, and a minus 1. So that's your square one there. So that's almost the same thing as the standard orthonormal bases, except they're jumbled, and some of them are hit with a minus sign. And then we've got 3, 3, 2, 0. And then we've got some other similar orthonormal bases that found by popping these things around. There we go. That was just to show you what the full SVD looks like in matrix form for that one that we did before. And I guess I should have done that before. But I just wanted to point out to you what this is showing right here. So the idea is the SVD works for any matrix. So not just for square matrices, not just for self-adjoint square matrices, but for any matrix, regardless of any kind of symmetry it may or may not have. Self-adjointness is a type of symmetry. And regardless of size and shape or dimension. So this makes it super useful for numerical methods and all kinds of other things.